What happens on the other hand if U0 is greater than energy? Well, that means we have something like the following case where the particle is going along. It encounters a potential that's rather large. And that's our energy level. Classically, this particle should stop right here and turn around. It should reflect off that barrier. It shouldn't be able to get through. But what happens quantum mechanically? Well, I'd still expect a sinusoid in this region. Because I have a potential energy of 0 over here. But how do we describe the particle in the region when the potential energy is greater than E? In this region, what do I have? I still have an equation that looks something like this. D squared psi equals minus k squared times psi. But in this case, what is k? It's 2m E minus U0 over h bar squared. Oops, over h. Notice that since E is less than U, this thing is a negative number inside the square root. And as a result, k is now imaginary. So I'm going to write that explicitly. I'll write it as I times a constant kappa. And therefore our differential equation looks something like kappa squared times psi. So the solution if this is x equals 0 is going to look something like a superposition of exponentials. Not sinusoids anymore because there's no I in here. Because what I was doing is the solution should have been e to the I or plus or minus I k prime x. But remember, in this case, k prime is I times kappa. And since there's now two factors of I, this just becomes straight exponentials. So this function over here becomes exponentially damped. So in the region before the barrier, it's a sum of e to the I plus or minus I kx, but in this region, it's e to the minus I kx. We can, in general, rule out one of these terms, either the first or the second exponential term, depending on if x is positive or negative, because we want the wave function to remain finite. So in this case, if this is the positive x-axis, we would generally rule out, or we would impose the boundary condition that capital A is 0.